So the point where we did somehow, and the last lecture was that how we could see the relationship of linear transformations in terms of matrix transformations. And the end of the lecture was that there are some properties of matrices can be related in terms of determinants in that sense. So we are going to relate linear transformations as some operations of some determinants, which will make a lot of things easier for us while we are going to solve some equations or relations for determinants. In the previous scheme of multilinear algebra or multilinear tensor products, here if we say, for example, if we assume that A is a linear transformation of n-dimensional vector space, of n-dimensional vector space, and if we let W as an alternating and linear form on V, and if we write AW, if we write this for a function such that is omega times AX1 and AX1, where is the an alternating and linear form of vector space V, and A bar can be sort of an alternating in that dual space, you can see it, linear transformation in such space. This A. So now what we are going to do is that if we assume a scalar such that a scalar has the properties of any matrix or any determinant, normally in a given vector space, when we have algebra associated to it, we have a scalar, a property of scalar which is identified and which is multiplied to a vector. Now the scalar we identify is a matrix or as a determinant in our next step. So there may exist a scalar, or there exists a scalar delta such that or is delta omega. So A goes to or A to first go to space, then we go to dual space, and then we go to delta. So we have associated a uniquely determined scalar delta with a linear transformation A on V, and delta is called the determinant of A, such that delta is determinant of A. So this is what I am saying. We associate a scalar as sort of matrices or as sort of determinant of A this thing. Such that there is scalar and we multiply it by a particular element AX is alpha X, Normally this value x, it can go from x1, x2, xn, and xn, and so on and so forth. Now if we assume that a bar of omega x1 xn is, so you can have, so if it's alpha 1, alpha 2, alpha n, so you can just take this scalar outside and you can have this as x1 and xn. Now this determinant of A, this scalar, you can write it as determinant of A is alpha to the power n. So different values of n will correspond to the different values of the scalars, and which will give the different the value of the determinant which is chosen as a scalar. And for example, in the simplest case, determinant of 0 is 0, and if it's 1, so determinant of 1 is 1. This. Now there can be various properties associated with this scalar or with this matrix or with this determinant, which we are going to briefly enumerate here. So if you are going to enumerate these properties, for example, and the simplest property is like that of, for example, so if omega is alternatingly and consists of alternatingly and linear forms, so you can have the property of you can have the property like C of omega xn. So you can have two elements, A and B. Normally you can have C, you can write a C, either it's A or either it's B. So you can have combination, C can be written into, so you can have two vector spaces, A and B. And A can be written in terms of scalar and vector, B can be written in terms of scalar and vector. And now you can have another C can be written in terms of A's and B's. So how we can have scalar addition and multiplication attached to, how we can see them. So if you want to write them C in terms of A and B, so you can write it like this: A B x n and A bar omega. And so we have a property of commutativity and associativity can, in terms of multiplication, which holds in the vector spaces. It should also hold in these the way we have defined here. And the scalars are taken as determinant of A and determinant of B. And we have to see determinant of C in terms of determinant of A and B. And the properties of associativity and commutativity, if they hold, it should be like that. So if you just have it, so you can have B bar, A bar, omega, x1, xn, such that C bar is B bar, A bar, or C bar omega is equal to, so now you can write this determinant as in terms of these two things. So you can write it as determinant of C into omega. So in the same way, C bar can be written as B bar, A bar, or omega, and determinant of C, you can write it as determinant of B bar, B and A bar into omega. So from this, you can say determinant of AB is equal to determinant of A into determinant of B. So this is an important property. So we can say determinant of AB. So it's like you are in the way we take A into B is normally A into B is A into B as a property individually as a part of multiplication. But here this property, so this also should hold for the determinants. If the determinants are like this, it should hold. So the point is, should it always hold or not? For example, if one of the two elements A and B are not singular, for example, if it's non-singular, how it has something to say about whether the elements, whether the property of linear dependence or linear independence can be seen here from this thing. If one of the two determinants may be non-singular, for example, if one of them is singular, so you can easily say the other may or may not, other should be non-singular. If both of them, so the point is that if one of them is singular, so you can easily identify as linear independence as a property can be seen. If one of them is singular and another is not singular, for example, so if I'll just write it here, that one which determinant of A inverse determinant of A is so if one of them is determinant and another is, so you can have this property. So normally A inverse should be equivalent to identity. Then only this property should so it's an identity element. So if determinant of A inverse is not equivalent to 0 and x1, x2, so on and so on is a basis in a vector space V, and omega is non-zero alternating n linear forms on V, then determinant of A is not equivalent to 0. This implies that the set AX1 is linearly is nearly independent, and we have also shown that if A inverse is 1, so it's also invertible in that sense. The property of invertibility and the property of linear independence, how they are related in a given basis. So from this we can show that A is invertible also. So if you remember, we had shown that A is invertible and there is some dual space. So from an invertible space you can come to an element in the original space. So that's the point. So if this property of determinants, if this property holds and then one of them is non-singular, then it should lead to this argument that A is invertible. And this property may be helpful very much later. So I only briefly say that it's helpful in the sense that, for example, you might be aware of how we solve linear equations in matrices or in the way we study Cayley-Hamilton equations. where we find the characteristic roots of a given equations. So in the same context, if you have a determinant, for example, for a fixed linear transformation, so I'm just you can read the rest of the thing. So the point is that we can even write these determinants as understanding them as linear transformations on these determinants. And in that context, so if for a fixed linear uh, transformation, A we can write as P minus lambda, where P is the function of scalar lambda, polynomial of degree n with the coefficients lambda and power n is minus 1. The way we had in that sense, that alpha to the power n, we had that scalar root in terms of n. So it gives a characteristic solution of that linear equation can be written in terms of lambda and a's. Then lambda is a scalar, so its value can go from minus 1 to n can go from 1 to whatever that is. So it's also called in literature, or its solution can be similarly omega y1 yn, where yi is equal to xi, and yi can be written in terms of, if you remember, as a part of this linear transformation, ei xi. Ei is basically, you can write it as a matrix, or you can write it as you can write it as a E, or you can write it as alpha ij of that element. And the characteristic solution will be determinant of A minus lambda is equal to 0 is the characteristic equation of A. Equation of A which has the characteristics roots. So the point to mention is that the linear, initially we started how we can write linear transformations as part of tensor products, and then those tensor products where basically they were part of two vector spaces, and at the end we could write them in terms of canonical functions as part of matrices. Continuing that, those matrices can also be represented in terms of determinants, and those determinants can be as if they are scalars of those linear transformations. And using the properties of these properties, we can arrive this understanding of it, and we can have solution of these equations, linear transformations in terms of these determinants which have those characteristic roots. Now the point is what are the proper values which may be associated once we have these characteristics values. Normally we take characteristic sheets or characteristic values, the proper ways to solve those Cayley-Hamilton equations. But what are the proper values? So a scalar lambda is a proper value, and a non-zero vertex and a non-zero vector x is a proper vector of linear transformation A of x is lambda of x. So almost every combination of adjectives, so whether we use adjectives of characteristic equation, eigenvalue equation, solution of the latent linear equation, circular equation, whatever eigenvalue, circular, latent, proper, and with the roots like the nouns like you have to find roots or value. So these all things come under the these all come under the thing something called proper values. What are the eigenvalues, solution, circular solution, latent, or how do you find roots which will correspond to the proper solution of these equations, which are in a sense seen as a part of linear transformations on those vector spaces, where those scalars can be assigned values. Sometimes they can be determinants, or in our previous case, or the scalars can be scalars. And for a so if there exists a non-zero vector for which Ax is lambda x, and a non-zero vector is proper vector of A, there exists a scalar lambda such that Ax is equal to lambda x. So sometimes the set of proper values which are assigned is of proper values of lambda of A are sometimes called spectrum of A. So if B is a linear transformation, B is any invertible transformation, then B inverse minus lambda. So it corresponded to that eigenvalue that the way we previously wrote about the equations. So you can also write it as B into A minus lambda into B inverse, where A minus lambda into x is 0 if and only if B into B inverse minus lambda into Bx is 0. So this means all of these equations are invariant if we don't have B. They are invariant if A is replaced by B inverse. Or if we have a linear transformation, Ax as lambda of x, so A square, so these are scalars, so it's like you can write it as A of x. So A of x you can have as lambda of x, it's lambda square x. We leave it. So these are some of the things. So you can say that there are some of the properties which you can read them yourselves in the book. So if there is a, for example, one further thing to show that if there are any, if there are any, so if let A be any net. So if let A be any linear transformation on an n-dimensional vector space and lambda 1 be its distinct proper values, and if we denote the algebraic multiplicity of lambda j, where j, the value of j can be from 1 to n, and m1 plus m3 goes to n, then we can write this equation for, we can write it as so on and so forth. Where its products of roots are, and the sum of roots are one second. So we can write it as like this. The function A is called, so we can write it as if let A be a union of an n-dimensional vector space and these are distinct proper values. We can write these in terms of this equation. Now there is also something called triangular forms. Triangular forms. It's the any linear equation having n eigenvalues. Now you can, so you can further show how we can construct triangular forms. Triangular forms. How we construct a triangular. Normally you have we will construct triangular matrices after some operations, and how we use the way we in a particular solutions of those determinants, how we can there is an echelon form of that equation, you might have an intuition of that, how we can have upper triangular form and lower triangular, how we can reduce the number of variables in a given n linear equations once we solve it. But in terms of linear, since we are just seeing it as a part of our understanding of linear transformation, so that if there is a triangle, how we can write the triangular form? Triangular form, if I just have it, so if there is a theorem, so if A is any linear transformation on an n-dimensional vector space, on an n-dimensional vector space, there exists n plus 1 subspaces So if there is an n-dimensional vector space, there exists n plus 1 subspaces m naught, m1, and mn minus 1, mn, with the following properties. Or, so if we enumerate them, mj, so j goes from 0 to 1 to n minus 1 to n, and dimensions of mj is I, and mg is subset of this m1 is subset of n minus 1 is sub. So proof of this theorem is you can write it. The important point is that how can these mj elements be written as for j going from 1 to n, and x is the elements of the vector spaces x1, x2 to xn. So, so how we can write axj as a linear combination of x1 to xj, such that the expression axj is alpha ig xi, and the coefficients must be I is greater than j, implies that alpha ig is 0, and in the triangular form we can write it like this. So our property of this Kronecker delta comes as a handy. So if we write alpha 1 1, alpha 1 2, alpha 1 3, so on, alpha 1 n, 0, alpha 2 2, alpha 2 3, 2 n, 0 0, alpha 3 3, alpha 3 n, 0 0 0, alpha n n. So the solution of this is basically A minus alpha I is 0 for I is equal to 1 to n. So you can construct both upper triangular matrices and lower triangular matrices. For a particular value of if this I is equal to j is 1, so these hold. So for these you can have this thing. So the best part of this thing is that a matrix is not triangular, but diagonal. Alpha ij is I is equal to 3. If a linear transformation such that matrix with respect to suitable coordinates diagonal, that's fine. This is how we can make a triangular forms. The other condition is that of nilpotence condition, which is also important. Nilpotence. The nilpotence condition is a to the power q is 0. So what's the condition that such that integer q is the index of nilpotence? So this condition is also very much helpful. How can we construct a nilpotence conditions to it? So there are various theorems to the effect, which I will just say to you, that you just as a PowerPoint exercise, that by induction how we can, basically there are n vector spaces and there are subspaces, and how we can exhaust those that entire space such that this condition is satisfied. That's it. And one interesting subtlety is of that of how we can construct Jordan forms. If you also remember previously the condition when we talked of the properties, this property, determinant of A, B is equal to determinant of A into determinant of B. The thing is that what's the condition that these should hold? So if one of the matrices between them is non-singular or singular, so it leads to some sort of uncomfortable adjustment, mentally uncomfortable thing, that whether it should be linearly correspond to linearly independent or not as a condition. If it's a non-singular, one of them is non-singular. So this appointment is like, for example, in linear transformations, can linear transformations being invertible and in some sense being non-zero, in some sense being, and how is it related with the idea of this, if we can construct nilpotent transformations in these constructions, such that if I just only read the theorem or write the theorem that every linear transformation A on a finite dimensional vector space is direct sum of nilpotent transformations and an invertible transformation. So every linear transformation on a finite dimensional vector space V is direct sum of nilpotent transformation and invertible transformation. So from this properties we have to use first just take this uncomfortable this thing that if one of them is non-singular, and if we construct a nilpotent condition like this, and from this you should be able to show that any linear transformation A on a finite dimensional vector space is direct sum of this transformation in a vector. So these two properties are somehow summarized here. So you can see to the proof of the theorem in the book, which is there, an interesting part of the theorem. And so the other part of the theorem too is that, for example, if I only read it, if A is a linear transformation on a finite dimensional vector space and lambda 1, lambda or lambda p are the distinct proper values of A with respect to algebraic multiplicities, then V is direct sum of p spaces of respective dimensions M1 such that Mj is invariant under A, that is A minus. So you can have n-dimensional spaces or n-dimensional vector spaces and their respective subspaces in their respective dimensions M1. So how are they invariant under A such that the condition of A minus lambda j is nilpotent on Mj on that subspace. So this is a subsequent theorem to this theorem 2. This is one theorem 1, it's theorem 2. So it's also interesting to see how the argumentation which has been there in the book, and at the end we can arrive at how we have Cayley-Hamilton equation. So from these two theorems, this nilpotent condition, this theorem and the other theorem, there are n subspaces, vector spaces which correspond to n subspaces in n dimensions, and how we can construct this nilpotent condition. So we can, and the subsequent theorem, we can arrive at something called Hamilton Cayley formulation equation, which we normally study as properties of determinants, but as a part of our understanding of linear transformations, we can arrive at then that every linear transformation is annulled by characteristic polynomial. So here we stop today's class.
mathematics.